And thank you to our speaker, Endi Kebede. This is our distinguished speaker talk organized by the Global Computing Lab. This is our second this semester, and we are thrilled to have a very talented junior colleague who is working in a topic that brings interdisciplinarity, in which computer science and machine learning and AI can do a lot to support. Our talk today is about learning how we can work together. And Eddie is here with us. He is a PhD candidate at the University of Delaware. He specializes in global irrigation and sustainable food water system. He holds 2 master's degrees in hydraulic engineering and irrigation engineering. And his research focuses on the development of global open source irrigation dataset and a comprehensive assessment of global water scarcity and its potential impact on food production and supply. We are thrilled to have you here, Eddie. Welcome, and you can start your talk.
Thanks so much.
Real quick before we begin, if anybody has questions afterwards, please use the question and answer function, and we'll be happy to talk with you. We'll have questions at the end, but please ask questions. We will have plenty of time for it. So thank you so much. Andy, go for it.
Thanks so much, Dr. Tafu and Michael. Can you see my screen?
Yes, we can.
Yes.
Yeah, thank you. Yeah, welcome everyone. Today, I'll talk about advancing high resolution of irrigation mapping with open source data and machine learning. So to give you a little bit of background, crop production is a widespread human activity that has been practicing for over multiple thousand years. And it's also central for feeding the ever-expanding global population, which is expected to be more than 10 billion by 2050. And from crop production, irrigation has a big share, which supplies more than 40% of the global food supply. The crop production in general and irrigation production in particular have several socio-environmental effects, both on positive and negative context. Some of them have the effects are natural resource, as crop production entirely depend on the availability of natural resources, including water and soil. Over utilizations of water for irrigation, especially in area where the extraction exceeds the recharge rates, might lead to depletion of aquifer, as well as depletion of other surface water sources. Not only this, but also crop production also depend on the use of artificial fertilizers, and the leaching of those fertilizers coupled with agricultural runoff have also caused the eutrophication as it observed in the case of Gulf of Mexico and many parts of the world. Crop production also have mostly a positive income on farmers, as it enables farmers to produce more than once in a year. That enable the farmers to enhance their income. But on the other hand, also it might also lead to income inequality, as marginalized land and marginal community might not be harness this benefit because it requires huge investment for laying out those irrigation practices. Crop production also might have a positive impact on nutrition, as the enhancement of crop production, particularly through irrigation, enables surplus food availability and stabilize the food prices, which enhance the access of the local community for different nutritions. But on the other hand, the specializations of irrigation production into a specific crop type, in a technical term known as monoculture, might also lead to micronutrient deficiency. Crop production might also have an impact on culture, especially particularly in dry climates. Those indigenous knowledge of dry land farming might be extinct through the introduction of irrigation. Not only this, but also the irrigation production and its coupled economical benefit might also lead to migration and other cultural shocks within that area. Crop production also affects the local climate, particularly it has a cooling effect. It also leads to cloud formation and disrupts the regular rainfall pattern. This impact can also cascade and have also further impact or effects. One of them is the resource competition. Irrigation productions constitutes more than 70% of the global freshwater. But there are also other sectors that require water, such as municipality, the industrial and electricity, and other industries that require huge amount of water. So in particular urban areas, there is a competition of water use between agriculture and other sectors that requires water. Land consolidation might also be one of the effects, cascading effects of crop production or irrigation production. Particularly the clustering of agricultural farming to large-scale farming for the purpose of mechanization and enhancing income might lead to the displacement of local community or affect the smallholder farmers. The tendency of farmers to shift more on cash crops, although it has a positive outcome on the economy, it might also lead to lack of diversity and the less availability of food crops in the regions that might also lead to food insecurity in some developing region. Irrigation production or crop production also have a broad impact beyond that on land tenure as well as rural and urban migration. So considering that irrigation has a deep implication, particularly for land and water sustainability, data foundation is a missing link to support this comprehensive relationship between crop production and other variables. So we need to understand the spatial distribution of irrigation. So the information, not only where is irrigated, but also when is irrigated and how much irrigated area on those specific equation is very important to comprehensively understand this relationship. However, such kind of detailed information on irrigation dynamics is generally limited. We have conducted a review study which is published in Nature Review Earth and Environment, which shows that most of the irrigation production data sets are either available at a coarser resolution, mostly at national level. Also subnational information might be available in some developed regions. And most of the census report, which is the main source of such informations, particularly in developing regions, are not updated even for the last 20 years, which make it very challenging to provide accurate and timely information how irrigation patterns have been evolved throughout years. One way of addressing it is preparing irrigated maps through the integration of several open source data sets and remote sensing technologies, which enables for assessing the environmental impacts of irrigation, as well as developing strategies for sustainable land and water management. General large-scale irrigation mapping can be classified into two broad categories. One of the category is census-based approach, where mapping of those irrigation highly depend on the availability and quality of the agricultural census data. Agricultural census is the collection of agricultural information through a comprehensive and total area coverage surveys. So those information usually conducted at 5 or 10 years interval, depending on which differs from country to country. So we have the census data, which mostly at national or subnational level, which is at a coarser resolution, and the census-based large-scale irrigation mapping involves downscaling of those national or subnational information into a grid cell information, and those downscaling involves apportioning, which is proportional distributions of those subnational and national irrigated area into a specific grid cell, so that the grid cell summed within the national or subnational area does not exceed the census report, or there is also a cross-entropy. Some of the data sets that developed using this approach include the area equipped for irrigation, which is developed by many scholars, including the most recent one, which is developed through our former lab member, Piyush. we also developed a new data set which was shared to the public earlier last year, known as Mirka OS, a monthly irrigated rain-fed cropped area. There is also another data set which is prepared using cross-entropy algorithm, which is known as MapSpam. So the advantage of census-based approach is the reliability of the data more or less is official, so a verified estimation of irrigation is possible. Not only, but also remote sensing approach, which I will discuss later, have a limitation on mapping crop-specific irrigated areas, but census-based approach enable to provide such kind of information. What are the limitations? The main limitation is most of the census-based approach have a lower spatial resolution. Most of them are in 5 arcminutes, which is vary according to latitude, but around the equator is like 10 kilometer by 10 kilometer grid scale, which is very coarse. Most of the census data sets are available every 5 or 10 years, which make it very challenging to update this irrigated area frequently. And its accuracy also depends on the integration of several other data sets as well as the census report. The other approach for mapping the irrigated area is remote sensing based approach. Remote sensing is the process of collecting information about the target object without being physically in touch, but rather using a sensor and collecting the amount of energy reflected or emitted from the target object. So remote sensing approach measures the amount of electromagnetic energy emitted or reflected from the target object and uses several passive and active sensors, whether the type of energy emitted is from sunlight or other sources. So by using open source satellite images or even source data source, which would be purchased, it enables the collection of several multispectral images from MODIS or Landsat or Sentinel-2, and these satellite images provide several bands, multispectral bands, where each bands represent the different ranges of electromagnetic radiation, and depending on this electromagnetic radiation range, the remote sensing approach classified into 3 categories. The first one is optical remote sensing, which includes the analysis of remote sensing in the near infrared, short-term infrared range. Thermal remote sensing includes the use of thermal bands for analyzing and developing evapotranspiration model or land surface temperature models. And the radar use a microwave electromagnetic radiation wave to extract soil moisture data and enable to predict the irrigated area. Particularly the optical one is the most common method because it enables to utilize the most common vegetation indices such as the normalized different vegetation index, the enhanced vegetation index, the green vegetation index, or other normalized different vegetation, normalized difference moisture index, or other vegetation index, and try to, as every target object such as plant, soil, water have its own spectral signature. And by using those spectral signature difference, it enables to distinguish irrigated area from non-irrigated area. So those 3 remote sensing categories can also further classified into 2. The supervised classification algorithm, which depends on using a labeled ground truth point to train the model in order to predict each pixel whether it's irrigated or not. Some of the most common method include random forest, support vector meshing, or neural networks, including CNN. Then supervised classification algorithm is just categorizing the spectral signature of each pixels, and the model will cluster them and classify whether it's irrigated or not. The advantage of remote sensing approach is high spatial resolution depending on the availability of the data. For example, Sentinel-2 satellite images provide a 10-meter resolution, which is a very fine resolution compared to the census-based approach. It also enables field-scale real-time monitoring. The amount of data availability compared to census is much frequent in remote sensing, because every 7 or 14 days, there is a possibility of getting those information and being able to monitor the agricultural field more frequently. However, it has also a limitation, particularly the optical remote sensing is affected by clouds. It also requires intensive ground truth point for training the datasets. And most likely, the amount of irrigated area predicted using remote sensing approach usually deviates from the official statistics. So I'll try to show you the irrigated area that we developed using both the census-based approach and the remote sensing-based approach. So the first one is the census-based approach, which we have developed to answer the main question of how have the global irrigated and rain-fed cropping pattern changed since the year 2000 to 2015. So to do that, we have collected a crop-specific irrigated and total harvested area census report from national census portals, or there are several national, international, as well as regional data portal which provide such information, including the FAO stat, Aquastat, Eurostat, and country stat. And these data sets provide a crop-specific irrigated and rain-fed area, and it's beyond. It's more than 175 crop types, so we reclassify them into 23 crop classes. Then we also use administrative boundaries from the Global Administrative Database Management Portal, which defines the administrative unit of each subnational unit for each country, which is very essential. And we also integrated with other graded datasets. When I say graded, it's just a TIFF file where the data is stored in each pixel. So the first one is a crop calendar, which defines the planting and maturity months of each crops, from which month to which month each crop is growing. Such type of information is collected from recently available dataset, which varies from year. There is also a graded annual harvested area dataset, which is gathered from the global agroecological zone datasets, which provide in each pixel the amount of total harvested area per pixel. And there is also a cropland extent. In each pixel, it defines the maximum extent or the maximum area per each pixel that's likely occupied by crop. And there is also another dataset, which was a bottleneck for updating or preparing this dataset, was the area equipped for irrigation. The area equipped for irrigation per pixel is in each pixel, which is 5 arc minute or 10 kilometer by 10 kilometer pixel, how much area is occupied by irrigation. So integrating this information and assigning a unit code for each administrative unit, and pre-processing those datasets, such as resampling, reprojecting, and other procedures, we try to downscale subnational statistics to a grid cell level, following a similar approach used for the previous version of MIRCA 2000. By doing that, we provided multiple datasets. The first one is tabulated data of crop calendar, which provide a subnational unit or national unit, a type of crop which grown on that specific area, the amount of irrigated area of that crop in that specific place, as well as the months in which the crop grown on that particular area. We also provide a gridded or a geographical TIFF file, raster file at both monthly and annual timescales. The pictures on the right side show you irrigated maize for the year 2015 and rain-fed maize for the year 2015. And in each pixels shown in a different color indicators the percentage of irrigated area, in this case maize irrigated area or rain-fed irrigated area occupied compared to the total pixel area, which is 10 kilometer by 10 kilometer. From that area, how much percentage of it is occupied by irrigated and rain-fed maize. And the data set is published in Nature Scientific Data, and the data is available in HydroShare. One of the advantage of our data set is we provide a fine-scale temporal resolution data set that such as at a Menzel scale, which enables to identify the temporal patterns of also cropping that changes from region to regions. For example, this is rain-fed maize, which shows the growing pattern, which changes from tropical to more the northern hemisphere. Generally, we saw that the irrigated area globally increased by 13%, and the rain-fed area increased by 15%. And rice is the dominant irrigated crop, and it remains dominant from the year 2000 to 2015, followed by wheat and maize. And maize showed a highest irrigated area percentage change around 24% compared to other crops. We also try to see how the irrigated area at pixel level, which is 5 arc-minute pixel, changed through time, particularly from the year 2000 to 2015. And you can see that in most parts of the Western United States, the central China, as well as the northern part of India, in this case, irrigated wheat showed a decreasing trend in 2015 compared to the year 2000. One of the limitations of preparing a global data set is its uncertainty depending on the quality of the census data as well as the other input data sets that we use. So to address that, we extensively try to validate our data set against other available or existing data set. This one is the previous version data set, and we try to assess the presence and absence map, which shows, for example, the agreement in blue showed both data sets showed at pixel level there is a specific irrigated area in some specific pixel locations, and the red one and yellow one showed there is a disagreement between two data sets. We also try to see at pixel level whether we try to be consistent with our other existing data set, which provide to be consistent more or less. And our data set is currently in HydroShare and recently published in Nature Scientific Data, as I mentioned earlier. Although those global irrigation mappings that I showed you earlier are very important, especially for assessing the global irrigation pattern at both spatial and temporal context, but the resolution is very coarse, which is 10 kilometers by 10 kilometers. That means there is no heterogeneity within that 10 kilometer by 10 kilometer location. And in some small countries, 10 kilometer by 10 kilometer might be larger than a county. So it didn't allow heterogeneity analysis within that 10 kilometer by 10 kilometer location. So a fine scale irrigation mapping is very important. Why we need it? Because it improves the spatial accuracy as it captures small scale irrigation farm level analysis. It also enables to capture heterogeneity, how the irrigation vary within a small spatial scale. And it also enables for usability in diverse range of application, including for precision agriculture, for monitoring the irrigation or agricultural practices at a field level more frequently compared to those global data sets that I showed you earlier. So how we are addressing or how we are advancing the global irrigation mapping, the current challenge is timeliness. That means census-based approach that I showed you didn't provide much updated information because the availability of census report is very limited and not updated frequently, and it takes 5 to 10 years to have the most latest census reported. Although there are a few remote sensing approaches that try to address those challenges, but often those remote sensing maps are not frequently updated. It's just like a single effort for providing those irrigated area for specific years. So how we address that? So to address that, we are proposing to provide annual maps from the year 2000 to 2013 at a regular annual updates through the integration of remote sensing in machine learning approach that I will discuss in a few minutes. The other challenge from the global datasets that I showed you or from other existing global irrigation mapping is existing products cannot support field scale monitoring. It's because the resolution is coarse. Most of the global existing irrigation datasets, particularly the census-based approach, have a coarser resolution, either it's 5 arc-minute or 13 arc-minute, which didn't enable to detect field scale spatial patterns of irrigated area. So in our approach, we are trying to develop a fine scale 30 meter and 10 meter irrigated area for those targeted here. The other challenge is democratization, the input data set, the code that used to generate the data, the ground truth level of those pre-existing data sets that are currently available, often not available for the general public unless you made official requests for those authors. And often also you didn't get a much positive resource. So we try to align with the FAIR data principles and the Mirka-OS datasets that I showed you earlier, as well as the data that we are currently developing. All the input datasets, the ground truth point, and the code will be publicly available. This enables for any scholars to regularly update those datasets whenever it's needed. The other limitation of the existing approach is computational agility. Most of the remote sensing approach typically start with the land use land cover classification and first identifying the cropland. It's computationally intense and it takes a lot of time for developing the cropland. In our approach, we're starting from existing cropland product and try to classify the irrigated area from that cropland product, which saves computational efficiency compared to the traditional approach. So to advance that, we are currently proposing to develop annual high resolution irrigation cropland for the 21st century from the year 2000 to 2030. So to tell you a bit about our approach, the first is collecting of the input data. The cropland extent dataset at a resolution of 30 meter pixels, whether that 30 meter pixel is a cropland or not in a binary classification, is extracted from the University of Maryland global cropland expansion dataset. Also the administrative unit and the satellite data is gathered directly from the Google Earth engine, which provide a few administrative boundaries. There is also a global agroecological zone based on other climate and other variables. It classified the global area into 33 agroecological zones. So those data comes from the FAO and international IISA. It's a combined effort which is led by FAO, and it providing the JZ version for data portal. The other important input data is the Landsat and Sentinel image, which is the satellite image. Currently, we are working on the Landsat 8, and we have a plan to extend it to Sentinel to have a more final version of the dataset. All these input data were gathered. Then, using the cropland extent, which provides any pixel which is cropland or not, and the global agroecological zone, we clipped or masked every cropland extent with an agroecological zone. Then we generate a random point at a specific interval of 5 kilometers, and a total of 4,057 random points were generated. Then these random points are to be a ground truth point, and we need to curate those ground truth points and label them whether it's irrigated or not. To consider that, we need a satellite image, and those satellite images currently from Landsat 8 were gathered from Google Earth engine, and it requires a pre-processing also, identifying the cloud threshold, also if there is any the atmospheric and other corrections necessary. Then we need to compute also monthly normalized different vegetation index. Normalized different vegetation index is one of the vegetation index which is calculated by the difference of near infrared and red divided by near infrared plus red, which enables to identify vegetation from non-vegetation fields. although NDVI is a primary index that enables to identify or characterize the field, there are also other variables that we consider. For example, using the satellite image, we try to identify if there are any nearest water source that are close to the field. Is there any visible farm structures? For example, central pivot can be easily seen from satellite, and most of the central pivots are irrigated. Is there any clear farm boundary that might be considered for irrigation? Is there any canal near to those agricultural fields? Those characterizations of crop field were also very important. Integrating the monthly normalized different vegetation index along with characterizing of the crop field using the satellite image that we extracted from Landsat 8, we try to curate each ground truth point, whether it's irrigated or not. The NDVI of irrigated land is expected to be higher than the surrounding area. But to enforce that also, we characterize, is there any nearest water source? Is there any canal, or is there any visible irrigated structure? So integrating that, we try to label or curate the ground truth point. And we have labeled ground truth point, a total of 4,057 ground truth point. And each ground truth point were also which was also characterized in the form of rectangle, were later divided into 30 metal grids, and that at a global level, a total of 852, and 25% of it, more or less, is for irrigated area, and the other is for non-irrigated area. Then it's just employing a random forest model. Random forest model is one of the machine learning models. Is simple learning algorithm that used to predict each pixel whether irrigated or not based on using several decision trees. So to employ to train and test the random forest machine learning model, we have to split the ground truth points into training and testing. So 70% of the ground truth points that collected and labeled was used for training, and the rest was used for testing. Then the next thing is train the random forest model. That means a Dryman's, currently what we are using is a Dryman's satellite image for a 2-month interval will be generated. And those NDVI of those Dryman's at a 2-month interval, which is differ from place to place, will be fused together for the model. Then the model, along with the ground truth point and the NDVI, will characterize each pixels based on their spectral signatures, as well as based on the characteristics of the ground truth point, and try to generate predictions of each pixel, whether it's irrigated or not. Then testing the accuracy is also very important. Currently, we're using the testing portion of the data set to test the accuracy of the data and compute the validation or the testing metrics, such as confusion matrix, producer accuracy, user accuracy, and overall accuracy. We also try to visualize and export the data if we believe that is sufficiently good enough in terms of accuracy. The other way of validating the data is also comparing with other existing data sets, which I'll try to show you in a few minutes. So we're having a preliminary result, which I believe is a good start. This is the irrigated area in the western parts of United States, which we believe that we capture most of the irrigated area of the California Valley, Snake River Plain, and other areas which we expect irrigated to happen in most parts of the western parts of United States. This lower image showed you the zoomed particular area and its corresponding satellite images. And as you can see, most of these fields are likely to be cropland, and our classification is within each cropland, whether the cropland is irrigated or not. But depending on the characteristics of each field in terms of NDVI and the collected characteristics of ground truth points, the model will level each pixel whether it's irrigated or not. And you can see that the overall accuracy, producer accuracy, and user accuracy of both irrigated and non-irrigated land in western part of United States was found to be good enough. Well, this is also the preliminary result for India. Most of the irrigated part of India is expected to be the north and northwestern part of the India, such as Punjab, Uttar Pradesh, and Bihar regions, which we believe that we try to capture. And this is also expected to have less or sparse irrigated area, especially in the eastern parts of the India, which we believe that more or less we try to capture in our model, and the overall accuracy is good. The producer accuracy for non-irrigated area might be less compared to the western part of United States, because India is have a wide range of agroecological zone, and we're still working on improving that accuracy. And you can see that this is the zoomed version for the state of Punjab, the zoomed a particular area of irrigated area, where this area might be urban area or other non-crop lands, and most of the area is irrigated, which is expected of those regions. So more or less the irrigated area, the predicted irrigated area for India, we believe that we capture it more or less with acceptable accuracy. In one of, we're also trying to develop the irrigated area in most sub-Saharan countries, including Nigeria. The irrigated area in Nigeria is more sparse. That's why I start with the state level, because when zoomed at the country level, the irrigated area is more sparse and it's difficult to visualize. Benue State, Nigeria is one of the irrigated, highly irrigated region, although highly might not be a proper term. And this generated data also showed you the distribution of irrigated area over Nigeria, and in this particular field, where you can see from satellite image near to the water source, showed you labeled by the model as irrigated. So currently, we are developing a preliminary result for some parts of the world, but also we are trying to also validate it against the existing data sets. Part of it is those existing data set is very scarce, especially for the year that we are preparing, since it is 2023. Currently, we are working on. So in a well-established country, such as India and United States, particularly, the irrigated systems is more or less stable. So it's fairly reasonable to see the spatial distribution of irrigated areas and comparing it with the closer year where the data set is available. So this is a comparison of irrigated area in Punjab, India, compared to the irrigated area of India for the year 2015 that the data is available, which is also prepared using a remote sensing NDVI threshold method. And more or less in terms of spatial distribution, 67% of the pixels in both data sets shows agreement. That means both data sets show irrigated area correctly, and there might be some disparities between those data sets in some parts of the location, particularly in some region where the other data set shows irrigated area where our data set didn't show. The same is true for California. There is a LANID dataset, Landsat-based irrigated area dataset, and we try to compare that also, our dataset also with that dataset. More or less, more than 70% of the pixel within our predicted outcome in California is well agreed with the LANID dataset, although there are some disparities in some parts of California, and more or less, we believe that the result is acceptable. The other approach is aggregating the generated irrigated area as national or subnational level and compare it with official statistics or even other existing data set. This is the irrigated area generated for Central Asia, particularly Kyrgyzstan and Uzbekistan. The map here showed agreement, disagreement maps between our generated data sets and the hydro solutions, which is a similar data set prepared for Central Asia for the year 2022. And we try to aggregate national and subnational level, particularly the national sum, and compare it with existing data set and official statistics. In most cases, our data set is much closer to the official statistics compared to the hydro solution existing data set. What are the key takeaways in future work? Mirkawa is a global crop-specific irrigated and rainfed monthly and temporally consistent new product for the 21st century. And to be consistent with the FAIR guideline, we make sure that the data, the code, as well as any raw data related to used for generating the data set is publicly available through GitHub, HydroShare, and other available data portals. The data products can underpin a new wave of assessment of land use, earth system, food production, and climate and beyond. Our next work, which we are doing in collaboration with Global Computing Lab at University of Tennessee, is preparing of a time series 30-meter irrigated area data set and refining the ground truth point to make sure this is robust, as well as integrating of other climate and soil data set in order to enhance the prediction of the model. Thank you so much.
Thank you so much for this presentation, Eddie. And I think we have some very interesting question for you. I want to start with a first question, and we are opening for discussion, by the way. So if you have question, you can put them in the Q&A, or you can raise your hand if you want to ask the question through the Zoom, through voice, and we will be pleased to listen to your question and have Andy answering. So let's start with the first question. It is about what are we looking for through this data set? Is it the level of water, something else? And is it 10 kilometer by 10 kilometer enough for what you are looking? So it's not about just irrigation, but what is that you are looking for from a practical point of view, and what is the potential of this irrigation, 10 meter by 10 kilometer by 10 kilometer, is it sufficient?
Yeah, that's a good question. Yeah, the first data set that I showed you, Mirkawa, as we call it, is a 10 kilometer by 10 kilometer data set, which is coarse if we're considering a field scale, but for global scale assessment, is considered a finer resolution because most of the global scale assessment, including climate model, is 30 arc minutes. So our data set is 6 times finer compared to those coarser resolution. But still, if we are considering a field scale, farm level irrigated area changes, then the global data set that I showed you, especially the 10 kilometer, might not be sufficient enough. But to assess, for example, how the global water scarcity evolves in relation to irrigation, how the food production evolves in relation to irrigation, or even how the climate evolves in relation to irrigation, especially in a model perspective, those data sets are very important. But if we are considering a very finer field scale assessment, the data sets that we are preparing in collaboration with your lab is, I think, a good solution to address those coarse resolution challenges.
So, and I have a question that follow up, because we have been working in the past with soil moisture prediction and also collecting data set from soil moisture. What is the difference between soil moisture study and irrigation study? Is there overlapping? Is it divergent goal for a computer scientist? This is a question that may be important.
Yeah, that's a very good question. Yeah, technical soil moisture is the amount of water that's present in the soil ozone, technically. So to do that, there are several ways. One of the approaches that I showed you is using a microwave SAR radar, and in order to identify the soil moisture using those microwave electromagnetic radiation. Soil moisture is essential to distinguish irrigated area, but not necessarily the existence of soil moisture showed irrigated area, because rain-fed area can also have a soil moisture. So how we can use soil moisture for irrigated area? Well, identifying the irrigated season. In a dry season where there is no precipitation, if the land is soil moist and we enable to capture that moist land, then that land is likely to be irrigated.
Thank you. We have another question from a participant is, what are the input features you use to train the machine learning model to distinguish between irrigated and not irrigated area? And have you considered way to prevent the model from becoming overly reliant on NDVI when identifying irrigation pattern?
That's a very
It's a
good
long question, but
Yeah.
it's also very interesting indeed.
That's a very interesting question. I think that's the part where Global Computing Lab and the University of Delaware is trying to address it, the limitation of the current approach, because currently the current approach is depending on first extracting the spectral signature of ground truth point to characterize that ground truth point labeled as irrigated and non-irrigated, and also fusing the normalized different vegetation index of the dry season, combining together and characterizing of those irrigated and non-irrigated area in terms of normalized different vegetation index. But to be fair and honest, the current approach is entirely dependent on any DVI. So in the adding of other variables, even vegetation index, such as normalized different moisture index or other climate and soil data set is, I think, the best approach to address that.
Thank you. We have another question. Is our attendees are really excited about this topic. So this is another question is, for producing result, does the region covered play a large role in the accuracy or quality of result? For example, you show some example highlighting specific area in the Western US and India. If so, what is considered for those analyzed region? For example, ecoclimatic feature of the region, availability, data for the region to produce label and train the model, etc. So again, what is the role of the specific region and what are the feature considered for the analysis of the region?
That's very interesting question. So yeah, when using NDVI for characterizing or labeling of irrigated areas, there are broadly two categories. One category is just generating the normalized differential index throughout the year and identify the max and mean and try to characterize, because the irrigated area is expected to have high NDVI, and characterize the irrigated area after analyzing the temporal curve NDVI curve of those specific area. In our current approach, what we are using is, first, we have a cropland. That cropland might be irrigated or non-irrigated, which give us a confidence because that's also a cropland. But we're also masking that cropland within each agroecological zone to make sure that we have representative random ground points. Not only that, but also the NDVI generated for dry season specific for each country or for each agroecological zone, because each agroecological zone have a different irrigation seasons. It might be April to June in some place, or it might be December to February in other places. So the dry months, which used for generating NDVI, is specific for each regions. So regions have a specific place. But in terms of accuracy, obviously, in some regions, the satellite image availability is very limited or it's very cloudy, especially in some irrigated, which might be challenging. Also, in some specifically, the tropical region is very easy to characterize irrigation because the irrigated is happening in a very dry season. But in United States and other parts of the Northern Hemisphere, the irrigated can happen even during some rain-fed region, which make it very challenging also to distinguish irrigated and non-irrigated area. So region has indeed have a great impact.
Thank you. Okay, next question. And this is also something that is related to the type of data you have, and it is, what do you think about including information from wireless sensor networks deployed on the field that monitor crops? Since this data usually consists of value, number, instead of images, would it be good to consider merging both data sets, image from satellite and value from crops? So we speak about heterogeneity of representation and combining the two.
Yeah. One of the challenge of preparing a global data set is the availability of the data varies from country to country. For example, a very advanced those wireless information might be available for United States, but it's certainly not available in most developing regions. So when you're developing a global data set, you have to make sure that you have a consistent methodology to make sure that the irrigated area classified in a consistent way. So even though those data is available and we know that it enhances accuracy, one way to address that is use that to develop a data set for a specific region in some parts of United States. But when you're developing a global data set, it's really challenging.
And I have a question about the machine learning method you're using. Have you tried other machine learning method aside from random forest? Would it be worthwhile to change the algorithm based on the region? For example, if you know a method tends to produce sharp boundary, then it may be more interesting for region where irrigation is more clearly defined versus region with large amount of rainfall or non-irrigation cropland. So machine learning, random forest, but can we have an adaptive selection of machine learning techniques?
That's very interesting. I think that's very. We have a plan indeed to have a cross validation of using random forest support vector machine and neural network and try to see whether the accuracy differs across different machine learning algorithms, which is yet to be done. But trying it for different region and whether which type of machine learning algorithm work for different agricultural zone is really a good recommendation and words to consider in our discussion next time.
Okay, I have a last question because then we have to wrap up. We are at the end of this interesting discussion. It is, what are the biggest source of uncertainty in irrigation mapping classification and how do you quantify them?
That's a very good question. Yeah, in irrigation mapping, the biggest uncertainty is the input data set, obviously. For example, we already have a big discussion with Global Computing Lab and the University of Delaware about the robustness of the ground truth points that we already have, because it's also subjective and it introduces some kind of error. So the way we classify irrigated and irrigated might differ from person to person, and that might also introduce some form of uncertainty. So the input data set is huge, including the census data, which varies from country to country in terms of quality and availability also. There are also some assumptions that we introduce while we're developing global data sets that might also introduce some form of error. Quantifying them is the biggest challenge. How much uncertainty there is per pixel is really challenging. What we are doing is just try to validate against existing data, against known ground truth points, and other data is the only way to check that.
Well, we are at the end of this seminar, and we have a couple of announcements that I pass to Michael. But first of all, I want to thank Endi for this fantastic presentation, for teaching us more about irrigation, its relevance, and the role that we computer scientists can do by working with you, your group, the group of Dr. Davis, who is present and is your advisor. So thank you, Kyle, for joining us today, and the community in general. So join me for a big round of applause for Endi. And I also want to thank all the participants because we were remotely today and we had fantastic questions that we want to follow up with Endi and Dr. Davis. Michael, what is our next appointment? What is our next distinguished talk?
Our next distinguished talk will be on March 20th, and it will be with Amy Roberts, a physicist from the University of Colorado.
Fantastic.
And so we're excited to see you all again, and it'll be a lot of fun.
And this time will be about not irrigation, but dark matter.
Dark matter, exactly. Yes,
it's more science fiction, or perhaps it's not science fiction. We will discover that in our seminar. Thank you, everyone. Thank you, Eddie, for joining. You are very welcome. It was a pleasure to learn from you today. All of you stay safe. It will be cold this week in Tennessee. Bye-bye.
Bye.
Thank you.